One of the most important applications of statistics is quality control. Suppose that you own a company that produces some car component. You want to produce good quality components that are not rejected by your client. You need to be reliable to be competitive. And the most cost-effective way for high quality is through constant monitoring of the production process. This monitoring is often done by sampling units of production and measuring some quality characteristics. The learning goal of these sections are to differentiate between common causes and special causes of variability of the output, to define R chart and determine the upper and lower control limits, and use the R chart to identify common and special causes. There are different causes of the output variability, and they are in general classified as common causes and special causes. Let's talk about common causes. The basic principle of control charts is that there will always be a variation in the output of any process. Some of this variation is due to inherent causes in the process that are difficult or impossible to specify. These causes are called common causes or chance causes. If these are the only source of variation, the process is in a state of statistical control or in control. Processes might become out of control at any time, and therefore they must be continually monitored. This is an example of how to monitor your output. So in this case, you are measuring the size of the tiles, and by setting one after the other in a vertical way, you can detect which ones are the ones that are out of size. Now, what are the special causes? Well, these are some special factors that produce additional variability. For example, a machine that is not working properly, an operator error, ambient conditional fluctuation, someone opened the door, the temperature changed, variation in the property of the raw materials, and so forth. These factors are called special or assignable causes. Special causes produce a higher level of variability than common causes. This variability is considered unacceptable. When operating under one or more special factors, we can say that the process is out of statistical control. Now, we have different ways of monitoring the system and identifying if the cause is a common cause or is a special case. The control charts enable quality engineers to decide whether a process appears in control or out of control. If the process is found out of control, the nature of the special cause must be determined and corrected to return to statistical control. So we have to identify if it was the door that was open or if the material it's faulty. So we have to identify what was the cause and correct it. Now, there are different types of control variables. We have continuous, binary, or count. And therefore, we have different types of charts. So in this class, we are going to concentrate on variable control charts, which are determined by continuous variables. Another type of charts are the attribute control charts, in case that the variable is binary or count. So how control charts work? Well, basically a control chart works similarly to a hypothesis testing. H null is the hypothesis that the process is in control. The control chart provides evidence of the truth of this hypothesis. So for variable control chart, we have the x-mean chart, the range chart, and the S chart for continuous variables. If we have an attribute control chart, that will be the P chart for binary variables and the S chart for count variables. Now, in the following cases, we need to identify if the variable is continuous, binary, or count. The first case is the number of flaws in a plate glass window. So how can we identify this variable? So the keyword is number, so therefore this one is a count variable. The second one is the length of time taken to perform a final inspection of a finished product. That will be continuous, binary, or count. Well, time is continuous, is the length of time. So this is a continuous. The next example is whether the breaking strength of a bolt meets a specification. So the answer of this case is it either meets the specification or not. So it's a binary. The last one is the diameter of a rivet head. The diameter is a real number, therefore it's a continuous variable. To collect the data, we take a number of samples over a period of time. These samples are called rational subgroups. All the variability between the units of a rational subgroup should be due to common causes and none should be due to special causes. There are two commonly sampling methods. First of all, you have your production time and you divide your production time in between a number of sampling times, and for each sampling times you're going to take some units and evaluate the quality. So in the first case, what you do is you take the units very close in time to the sampling time, and in the second case your units are taken equally spaced in time in between the sample times. So these distances are the same. Now, for variables data, the number of units, so the ones in green, the ones that you evaluate at every sampling time, is a small number and is usually between 3 to 8. So these numbers are between 3 and 8. And the number of samples in general should be at least 20. So these sampling times should be at least 20. And it's best to take many samples taken frequently rather than a few less frequent samples. If you have binary or count data, so your samples must be in generally larger. Control versus capability. Now, there is a difference between process control and process capability. Let's review what is to be in control. A process is in control if no special causes are present, only common causes. So the distinguishing feature between a process that is in control is that the values of the quality characteristic vary without any trend or pattern. For example, if we are measuring some diameter and that's something like that, and if we have a special cause, so special cause means that when we are measuring there is something like sticking out, like out of the standard variability that we normally see in our system. But it is still possible to look like this, to be like in control, but to not meet the given specification. Let's have an example. Let's say that in a process we are measuring steel rods, and the length vary randomly in between 19.9 and 20.1. So these values. So we are measuring and we see that the values are over there. However, the design specification calls for a length between 21 to 21.2. So this is what actually is required to have. So we can see that the process is actually in control because it's varying in between small values, but is not meeting the specification, so it's not the final result that we were expecting. So capability is the ability of a process to produce output that meets a given specification. Okay, it's in control and meets the specification. Now we have a set of questions here. What I suggest is to pause the video and answer each one of these questions. The solution to this question is given in the slides that are posted in Blackboard. Control charts for variables. Assume that in a process, each of the samples are from a normal population with mean mu and standard deviation sigma. The quantity mu is called the process mean and sigma is called the process standard deviation. Now let's have a look to this table in which I organize the different samples. So we are going to have a number of samples like from 1 to n, and this number is about 20, 30. And each sample consists of monitoring from 3 to 5 units. So we have the different values, and for this particular sample we compute the mean and we compute the standard deviation. Now this mean is called the x1 bar because it's the mean of sample 1, and we do the same thing for sample 2 up to sample n. So at the end we are having a collection of means for every sample and a collection of standard deviations. The idea behind a control chart is that each value of x approximates mu, the population mean or the process mean, and R and S approximate S. So R is the range, we're going to go in detail with that one, and S is the standard deviation, and this standard deviation approximates the standard deviation of the process. If the process is in control, the process mean mu and the standard deviation sigma are the same for each sample. If the process is out of control, the process mean or the process standard deviation sigma or both will differ from sample to sample. So we need to monitor that they remain approximately the same. Now we have three different types of charts. We have the range, the standard deviation, and the mean. Now the R or S chart is first used to measure and control the variability of the process, and then an X chart is used to control the process mean. So we only need R or S and then X. And the basic assumption, remember, is that the measurements follows an approximately normal distribution. Now let's have a look to the data collected in example 10.1 in the book. So these are the different samples. We have 32 samples. These are the sample values. This is the mean of every sample. So this is this plus this plus this plus this plus this divided by 1, 2, 3, 4, 5. So this is the mean of this sample. Now how do we get to the range? To find the range, so we look for the minimum in the sample. So the minimum value is 1.88, and we look for the maximum value. The maximum value is 266. So this is the minimum value and this is the maximum value. So the range is equal to the max minus the mean. In this case we have 2.66 minus 1.88, so we do the math and the result is 0.78. So 0.78 is the max minus the mean. So that's the range, which is an approximation of the standard deviation. Now the standard deviation is computing in the traditional way, so it's the sum of x minus the mean, xi minus the mean, divided by, in this case is 1, 2, 3, 4, 5, minus 1, and the square root of that one. So that's the standard deviation that is calculated in this case. So we are computing 32 means, one for each sample, 32 ranges, and 32 standard deviation. Then we take this value and they compute the mean of this column. So that's the mean of the means. That's why the double bar. And this is the mean of the range. So that's the mean of this value. And this is the mean of the standard deviation. Now remember that x approximates the process mean during the time the sample was taken, and R and S approximates the process standard deviation. So if the process is in control, then the process mean and standard deviation are the same for each sample. Now, saying that are the same means that X, R, and S will be contained within some computable limits, and those are called the control limits. Now, how do we define the control limits? So let's say that we have the R chart. So we have on this axis the sample number. So we have from 0 to 33 samples, and for each value we plot the value of the range for each one of the samples. Okay, now these lines corresponds to the mean, and this line corresponds to the UCL or upper control limit, and this line corresponds to the lower control limit, and they actually corresponds to 3 times the standard deviation distance from the mean. So saying that our values are in between this distance is saying that they are. How do we compute the upper and lower control limits? We use table 810, control chart constant table. So D3 and D4 are estimations of the range, the R chart, of the population mean, whose values depend on the sample size n. So the upper control limit, mu r plus 3 sigma r, is estimated with constant D4, and mu r minus 3 sigma, the lower control limit, is estimated with D3. So it's very simple. The upper control limit is just D4 multiplied by R, and the lower control limit is D3 multiplied by R. So in this particular example, so D4, we look into the table. So the table has some constants, A2, A3, B3, B4, D3, D4. The key point is that our number of samples is 5, so this is our line of interest. We are looking to D3 and D4. So D3 is 0 and D4 is 2.114. So these are the estimations for the R chart. So let me keep it here. So D4 times the mean of R is equal to 2.114 D4 multiplied by the mean of R, and if we go back to the table, that's 0.607, and this is equal to 1.282. So if you don't remember where this value came from, the R bar, let's go back to the table, and this is the mean of the column of range of all the samples. Now the lower limit, so the value of the constant D3 is 0, so it's equal to 0 multiplied by R mean which is 0.607, but 0 multiplied by anything is equal to 0, so this is equal to 0. So the lower limit is 0 and the upper limit is 1.282. So those are the values in this chart. Once you compute the upper control limit and the lower control limit and you plot your data, you have to identify the points that are out of the limit. In this case, it corresponds to this sample, so that's sample number size. So you have to look and address what is the problem with sample 6, what happened in that moment. The door was opened and the material wasn't the right one, anything that could happen, and then you remove it from the list, and then you have to recompute your table by removing this sample and addressing what you had to address. You have to recompute everything for your new R chart, and in this case we can see that all the points are in control, and then we can proceed to analyze the mean, and we will address that in the next video.